Hi, it's Double O Pi, your undercover chemist here. Today, we're going to be balancing redox reactions using the half reaction method. We're going to do this in both acidic and basic medium. But first, let's start off with a review of redox reactions. In a redox reaction, there's a transfer of electrons so that one substance loses an electron and its charge becomes more positive. This substance that's losing an electron is undergoing oxidation, and we call it the reducing agent or the reductant. We also have a substance that's gaining an electron, undergoing reduction. The charge on this substance becomes more negative, and we call this the oxidizing agent or oxidant, because it is causing the other substance to be oxidized. So here's an example of a redox reaction. We know it's a redox reaction because the two substances are changing in charge. But if you look at this reaction, you realize it can't be balanced. For one thing, where did the oxygens go? There are oxygens on the permanganate ion, but there are no oxygens on the other side of the reaction. And if you calculate the oxidation numbers, you'll see that the oxidation numbers are changing by different amounts, and so according to this reaction, different amounts of electrons are being exchanged. And that can't happen. We can't exchange different amounts of electrons because electrons don't float around in solution the way that ions do. One of the fundamental rules of balancing a redox reaction is the number of electrons that come off the reducing agent has to equal the number of electrons that go on the oxidizing agent. So what we're going to do is we're going to look at the oxidants and the reductants separately in what we call half reactions and look at how each of those substances interact with the solution around it. So one thing about redox reactions is that they frequently happen in aqueous solution. And we're going to take advantage of this fact to help balance them. We're going to start by balancing equations in acidic medium, and we'll talk about what that means in a little bit. As you can see, balancing a redox reaction has a lot more steps than just balancing a regular equation. And although there are quite a few, let's try and simplify this by breaking it down into three separate sections. The first section is to break the whole reaction into half reactions, an oxidation reaction and a reduction reaction. The second section, we're going to balance each of those half reactions. And the last part consists of taking those balanced half reactions and integrating them into a balanced redox reaction. So let's go back to this equation that we were looking at earlier. We have permanganate ion reacting with the chloride ion to make manganese 2+ and chlorine gas. So let's start writing our half reactions, and we're going to do that by looking at the species that are present in solution. And you can see that these two species both have a common element. They have the common element of manganese. So most of the time we're going to be looking for something that's not hydrogen or oxygen, although that doesn't always work. And of course, then if you look at what's left, we have the chloride ion and chlorine gas, and both of these contain chlorine. So our two half reactions will be as follows. We're going to have our chlorine half reaction where a chloride ion will turn into chlorine gas, and we'll have our manganese half reaction where our permanganate ion will turn into manganese 2+. Which of those is the oxidation reaction and which is the reduction half reaction? We don't know yet. We'll find out. Now we're going on to the second section, which, if you remember, is balancing each of those half reactions. So we're going to work on each of them separately. Let's start with the chlorine half reaction. So the first step in this section of balancing a half reaction is to balance atoms other than hydrogen and oxygen. So if you look at this, the only atoms we have are chlorine atoms, and on the left side we have one chlorine atom, and on the right side we have two chlorine atoms. So we're going to balance those by adding a factor of 2 on the left side. Now we're going to balance the oxygens. Well, that's pretty easy for this half reaction because we don't have any oxygens on either side, so we can skip that step. Do we need to balance hydrogens? That's the next step. No, there's no hydrogens here. So this is a very easy half reaction, which is why we started with it. Finally, we're going to balance the charge by adding electrons. This takes into account the fact that a redox reaction has electron transfer going on. So let's look at the charge on both sides of this reaction. The chloride ion, as you can see here, has a negative charge. So the total charge on this side of the reaction is -2. We have 2 chloride atoms. Each of those chloride atoms has a -1 charge. 2 times -1 is -2. On the right side, we have 1 neutral molecule, so its overall charge is 0. So you can see that we don't have the same charge on each side of the reaction. And that charge needs to be balanced. That's one of the elements of a balanced equation. So we're going to balance that charge by adding electrons. Remember that electrons have a negative charge and will reduce the overall charge. We're always going to add electrons to the side that has the higher charge. On the left we have a -2. On the right we have a 0. That's the higher charge. So we're going to add 2 electrons. And if you recalculate now, nothing's changed on the left side of the equation. But now the right side, our math says we have 0 plus 2 times the -1 charge from our electrons. Now that also adds up to -2. So now we're good with this half reaction. Let's go on and balance our manganese half reaction. We have permanganate here on the left side and manganese 2 plus on the right side. And we're going to start by balancing the atoms other than hydrogen or oxygen. And that's going to be manganese here because this is a manganese half reaction. So luckily that's already done here because we only have 1 manganese atom on each side. Let's go on to step 3. Remember, in step 3, we're balancing the oxygens by adding water. This was one of the reasons we realized our redox reaction wasn't balanced. We have oxygens on one side and not on the other. When you balance a normal equation, you can't add things to it or take things away. So why do we do that in redox reactions? The answer is that we are balancing this in the environment of an aqueous solution. Everything is dissolved in water. And since it's dissolved in water, there's water everywhere, and that water is always participating in the reactions. So it's not that the water is appearing out of nowhere. You can see right here in our equation, both of these species are aqueous. That means they have water surrounding them. So we're going to add some water. We have 4 oxygens here on our permanganate ion, so we need 4 oxygens on the other side because there's no oxygens there currently. So we're going to balance this by adding 4 waters to the product side of the reaction. Now you can see we have 4 oxygens on the left side, 4 oxygens on the right side in the water. So that's great. We have balanced the oxygens. But you'll notice that when we did that, we didn't just add oxygen to the product side. We also added some hydrogen. So now our hydrogens are out of balance, and that's why we add H plus ions. Why can we do this? Once again, we're adding something that didn't used to be there. But remember, we're balancing this in an acidic medium. In other words, in an aqueous solution that contains acid. And acid solutions have H plus ions. And so there will always be H plus ions around. And that's why we can add H plus ions. So let's do a hydrogen accounting. We have no hydrogens on the left side. We have 8 hydrogens on the right side, 2 from each water molecule. And so we need to add 8 H plus to the reactant side of our equation. There's our 8 hydrogens. Now we're going to move on and balance our charge by adding electrons. So let's look at our charge math. On the left side, the reactant side, we have a -1 charge from the permanganate. We have 8 hydrogens, which each have a +1 charge. So overall, we have a +7 charge. On the right side, the product side, we have +2 from the manganese 2+, and we have a bunch of neutral water molecules, so our overall charge is +2. Now, we need to balance this charge by adding electrons. Remember, we always add electrons to the side with a higher charge, so we're going to add 5 electrons. And if you check the math once again, you see that now we have a -1 charge from the permanganate, 8 + 1 charges from the hydrogen, 5 - 1 charges from the electrons, and that gives us a total of +2. Of course, the right side does not change. That's also still +2. And now our charge is balanced. So now we've balanced both of the half reactions. Let's talk about how we put those together into one reaction. So here are our two half reactions. How do we know which is the oxidation and which is the reduction? Well, you could tell by looking at where the electrons are. So in this case, the permanganate ion is gaining 5 electrons. The permanganate plus 5 electrons makes something else. And in the other half reaction, the chloride must be losing electrons, because you can see that in the final state of the half reaction, the electrons are separate from the chlorine species. That is an oxidation reaction. Losing electrons is oxidation. So remember what I said, that however many electrons come off what's being oxidized has to be the same number of electrons that go on what's being reduced. Now, how can we do that? You can see there are different numbers of electrons here. So what we're going to do here is we're going to look for the least common multiple. And the least common multiple here is 10. 5 times 2 is 10. And so we're going to take each half reaction and multiply it by an appropriate factor so it ends up with the least common multiple for the number of electrons. So for example, for our first half reaction, we're going to multiply that by 2. Everything in that reaction is going to happen twice. You might think of it that way. So 2 permanganates will react with 16 hydrogens and gain 10 electrons to make 2 manganese 2 plus and 8 waters. And we could do the same for the chlorine, except chlorine we're going to multiply by a factor of 5. Okay, so here's everything all multiplied out. And now we're going to add those half reactions together and simplify them. So to add them together, look at everything that's on the left half of the arrows in both half reactions. That's going to be what you have on the reactant side of your complete equation. And then take everything that's on the right-hand side of your reaction for both half reactions, and that's what's going to be on your product side of the complete reaction. So as you can see, this is going to be a mess. We have all of this stuff, and now we're going to simplify. And this is just like doing a net ionic reaction. If you see something on both sides of the equation, it will cancel out. So in this case, we have 10 electrons on each side of the equation, and that is one indicator that you are doing this correctly. When you get to the step, your electrons should always cancel out. If they don't, go back to step 6 and get the appropriate least common multiple for your factors. So now we can simplify it further, and here you see the final balanced equation. All right, let's try another problem. Here we have nickel oxide reacting with chlorine gas to make chlorate ion and nickel 2 plus. And we're going to start out by writing the half reactions. So once again, we're going to look for common species. Here we have our 2 nickel species, and we have our chlorine species. So those will make up our half reactions. A nickel half reaction and a chlorine half reaction. And once again, we don't know which one is the oxidation reaction, which is the reduction reaction. But we'll figure that out as we balance our half reactions. So let's go through and balance the half reactions. We'll start with a nickel reaction. First of all, we balance the atoms other than hydrogen and oxygen. And since this is a nickel reaction, that means we're going to be balancing the nickels. They're already balanced. Now we're going to balance the oxygen. We have 2 oxygens on this side and none on this. So we're going to add 2 waters. That will give us 2 oxygens on the product side as well. Then we're going to balance the hydrogens by adding H+. Well, let's see, we've got no hydrogens on this side, but we have 4 hydrogens on this side, 2 from each of the waters. So we need to balance that by adding 4 H pluses on the reactant side. Now we're going to balance the charge by adding electrons. Let's look at our charge math. On the left side, we have a neutral nickel dioxide and 4 hydrogens with a +1 charge. So we have a total of +4 on that side. On the right side, we have a nickel atom with a +2 charge and 2 neutral water molecules. So that gives us a +2. So we'll add the electrons to the side with a higher charge, which is the reactant side. So this is our reduction reaction. And then if you look at the math, the right side hasn't changed. The left side has, and they now both add up to +2. Let's look at our chlorine half reaction. Do we have a balanced equation here? Well, we have 2 chlorines here. We only have 1 chlorine over here, so we obviously need a factor of 2 on the product side. Now let's balance the oxygens. We have no oxygens here. We have 6 oxygens on the right side because each of those chlorate ions has 3 oxygens. So we're going to have to add 6 waters to the reactant side. Now let's balance our hydrogens. We have no hydrogens on the right side, but we do have 12 hydrogens on the left side, 2 from each of the water molecules. And so let's add 12 hydrogens to the product side. Finally, we're going to add electrons. On the left, we have a whole bunch of neutral species, so that's easy math, 0. On the right side, we have 2 chlorate ions with a -1 charge, and we have 12 hydrogens with a +1 charge, so that's +10. Now, which of those has a higher charge? Obviously, it's the +10 side. So we're going to add 10 electrons to this side, and check your math. Now it comes out to 0. The left side hasn't changed. That's 0. Our charge is balanced. Let's put these together. Once again, we're looking for a least common multiple. We have 2 electrons in the first equation. We have 10 electrons in the second equation. So our least common multiple is going to be 10 again. Let's multiply the first half reaction by 5. The second one is already at 10, so we don't need to multiply by anything. Or it's just a factor of 1 is another way of looking at it. And what do we get? Here's everything multiplied. And now let's put them together. Take everything on the left side to make your reactant side. Take everything on the right side of the arrows to make your product side. And you end up with a huge equation, which obviously needs some simplification. So we have our electrons canceling, which of course is the sign that we have everything done correctly. We have a bunch of hydrogens. Now, these don't cancel out completely. The ones in the product side of the reaction all disappear, but we're still left with 8 hydrogens on the reactant side, because only 12 of those hydrogens cancel out. If you look at the waters, all of the water in the reactant side cancels out. 6 of the 10 waters in the product side cancel out. That leaves us with 4 waters. And so now, here is our simplified equation. So up till now, we've been talking about balancing things in acidic medium. What happens if you don't have any acid? What happens if you have base instead? The answer is we can also balance equations in basic medium. The difference is in basic medium, you don't have any H+. You have OH- ions, hydroxide ions instead. So we have a scheme for balancing redox reactions in basic medium, and it's fairly straightforward. You'll notice that there are more steps than there were before, but all of these steps are exactly the same as balancing a reaction in acidic medium. So essentially what we're doing here is balancing a reaction in acidic medium and then adding an additional step. So let's go back and let's look at the reaction we just balanced. Here's a reaction that's been balanced in acidic medium. We're going to just go through and do the final step, the additional step, to transfer it to basic medium. And essentially what we're going to do is look at everywhere there's an H+, and add an OH minus to cancel it. So we have 8H plus right here. We're going to therefore add 8 hydroxides to cancel that H plus. And since we're adding them on one side of the equation, we're also going to add them on the other side of the equation so that this is the exact same reaction. Now, why would we do this? The reason is that if you put together H plus and OH minus ions, you end up with water. So if you see 8 H plus ions and you add 8 hydroxides, those are going to combine and turn into 8 water molecules. So now here's what we have for that equation. You'll see that all the H plus is gone. We have OH minus instead. So that's great. That's what we'd expect to see in basic medium, where there is a lot of water present and also hydroxide ions. But you'll notice that by creating those new water molecules, now we need to simplify again. So we can cross out some water molecules here. All of the waters on the product side go away. They leave us with 4 water molecules in the reactant side. And now here's our new reaction in basic medium. And again, look at these equations. These are the same equation, one balanced in acidic medium, one balanced in basic medium. What has changed? If you look at the reactants, you see that they combine in the same ratio, whether it's balanced in acidic or basic medium. And the products, same thing. They are produced in the same ratio, no matter what medium this is occurring in. The water is always present. So really the only thing that has changed is whether we have H plus or OH minus present. H plus in acidic medium, OH minus present in basic medium. That is the only difference between these two ways of depicting the same reaction. So let's do one more example. This time we'll go from start to finish and end up in basic medium. Here we have perbromate reacting with lead 2 plus to make solid lead 4 oxide and the bromate ion. So we're going to have a lead half reaction and we're going to have a bromine half reaction. Here are our half reactions. Now let's go through and balance them again. Start with lead. We have 1 lead on either side, so we're good there. For oxygens, when it comes to oxygens, we have 2 oxygens on the product side, none on the reactant side, so let's add 2 waters. And balance the hydrogens. Now we have 4 hydrogens on the reactant side, none on the product side, so we're going to add 4 hydrogens. Now let's balance our charge. On the reactant side, we have 2 neutral waters and a +2 charged lead, so that gives us a +2 total charge. On the right, we have a neutral lead 4 oxide, and we have 4 +1 charged hydrogens, so that gives us a +4. We're going to add electrons to the more positively charged side, so that gives us 2 electrons here. Double check the math. Now we have 2 electrons with a -1 charge, 1 neutral lead oxide, and 4 +1 charged hydrogens. That gives us a +2 charge. We still have a +2 charge on the left, so now we're good. There's our first half reaction. Now let's look at our bromine half reaction. We have 1 bromine on either side. We have 4 oxygens on the left, 3 on the right. Let's add a water. Now we have 4 on both sides. Let's balance our hydrogens. We have 2 hydrogens on the right side, none on the left side. So we'll add 2 hydrogens. Now let's balance our charge. We have a -1 charge on the perbromate, plus 2 +1 charges from the hydrogen. So +1 charge there. On the left, we have a -1 charge from the bromate and a neutral water molecule, so that gives us a -1 charge. Add electrons to the side with the highest charge. That would be the left side here, so we're going to add 2 electrons. Check your math. Right side hasn't changed. left side, we now have -1 from the perbromate, 2 +1 charges from the hydrogen, and 2 -1 charges from the electrons. That all adds up to -1. So we have -1 on both sides. We're good. Let's put those together. Here are our two half reactions. We have the lead half reaction, which is an oxidation reaction, and we have the bromine reaction, which is a reduction reaction. Let's find our least common multiple. 2 electrons on the first reaction, 2 electrons on the second reaction, so conveniently our least common multiple is 2. We don't have to multiply by anything. So let's add our half reactions together and simplify them. This is what's going to be on our reactant side. Here's what's going to be on our product side. And putting them together, this is what we get. Let's simplify. Electrons cancel. Yay. All of the hydrogens on the reactant side cancel. 2 of the 4 hydrogens on the product side disappear. So that gives us 2 hydrogens total. 4 waters. All of the water on the product side goes away. 1 of the waters on the reactant side goes away. 1 water molecule on the reactant side. So here's the simplified reaction. But that's balanced in acidic medium. Let's get it balanced in basic medium. Now let's add the hydroxides. Well, we have 2H plus here, so we're going to add 2OH minus. And since we're adding it to one side, we'll also add it to the other side. That 2H plus 2OH minus in the product side will turn into 2 waters. We can simplify those waters. And this is our final balanced redox equation. Thank you for watching. Please check out the other problem-solving videos on the 00 Pi YouTube channel.